All right. Good morning, everyone. Welcome to day 2 of I3D 24. We'll begin, as yesterday, with our keynote, our second keynote. So it's my really great pleasure to have Sylvain Lefebvre here with us. Sylvain is a research director in here.
Recording in progress.
In here, Nancy. He's the leader of the MFX group. MFX stands for Metaphron Graphics, correct? So he does a lot of work on fabrication and additive manufacturing, which is, I think, not what he's going to talk about today. No, not at all. So it's I'm also super excited because I will not give you any spoilers, so I will let him talk. But apart from his great work, I think I was trying to remember the year, but I could not. So I know the decade, so it's like somewhere between 2005 and 2010, I met Sylvain in Sofia Tivoli. And I was doing a lab tour, and then I was talking to him about his work. But another thing that really impressed me was all the care and attention he put in presenting his work. He was telling me how he did the capture with another video card and then edited and all the things. And I was super impressed with not only the texture work he did, but how you presented. So I'm super excited because I know he puts a lot of enthusiastic and work in his presentations also. So Sylvain, it's a great pleasure and honor to have you here. Please, the floor is yours.
Thank you. All right, thank you very much for the introduction. I would like also to thank the organizers for inviting me today. It's always a great pleasure to attend I3D. Yesterday was very inspiring. I'm sure today will be as well, and I'm going to try to contribute to this with this perhaps somewhat unusual keynote, because I'm not going to talk about my main research area. Instead, I'm going to talk about a passion project of me that I started about 6 years ago, and which is to take a deep dive into hardware design with the objective to do graphics. So I want to share with you some of this interesting topic, I hope. So what I mean by that is, and the way I approached the project was to start to revisit some good old milestone algorithms. For instance, the famous recaster that is at the root of the Wolfenstein 3D game. So what you see here is a pure hardware reimplementation. There is no CPU. This is all done with gates, logic, and clocks. Here is another case. Here there is a small CPU which is accompanied by a bespoke GPU that can render a level of Quake on this tiny screen, and the entire hardware fits in the USB port. You don't see it because it's inside the USB port, and I will show you the board being used afterwards. So that's how much Quake you can fit in a USB port. Here is a partial differential equation being solved real time on hardware, no CPU again. This is all done directly through, again, logic and clocks, and I will explain to you how this is achieved. And finally, I really wanted to open this door. It took me 30 years or so, but now you can open the door and you can explore the landscape behind. And this is, again, a small CPU accompanied by a bespoke GPU that assists the CPU in rendering the Doom level. So this is Doom accelerated by a GPU. All right, and how do you do your own hardware? That might seem a bit mysterious. I mean, of course, you could take your soldering iron and solder gates onto a custom PCB. That would take some time. In principle, it should work. It might be slow to do, and also the hardware will be limited in frequency, but that's not how we do this. The way you can do it in 2024 is through the use of FPGAs. I'm sure most of you have heard this name, but if you're not familiar with the concept, an FPGA is like a shape-shifting circuit. So you can reconfigure it to become any hardware you want. And if that sounds mysterious and magical, don't worry, because we're going to take a deep dive into FPGAs, and I'm going to explain exactly how this works. And you'll see that it's, in fact, a fairly simple and clever idea. And so through these devices, you can generate your hardware, configure the FPGA to become your hardware, and there you go. You have a circuit that will execute exactly what you want. All right, so at this point, hopefully some of you are thinking, okay, that sounds pretty cool, but probably most of you are wondering, why would you ever do that, right? I mean, what's the point? So I had a full list of reasons, but in the interest of time, I had to select only 3. So here are my top 3 reasons. The first one is for education purposes, to educate yourself and to educate others about what is a computer at a fundamental level. The problem with modern computers is that, when you explain what's going on to students in a computer, and then they look at their own computers, it's very hard for them to relate the concepts you're talking about. with what's going on their actual very complex machine. By being able to redo simpler computers from scratch, simple but non-trivial computers. By that I mean, things where you can compile code with GCC and run it on your own hardware. You can really create a situation where the students can look into this, they can understand every small mechanism inside, they can start to hack it, they can start to improve it, and they can immediately interact at the frontier of hardware and software, which I think is really cool and is a much better way to talk about computer architecture than working only at the abstraction level. The second reason, which really motivated me, is to get back the freedom to hack. In the 80s and 90s, when I learned programming, the computers were fairly simple, and in particular, you were very close to the silicon. So there was very few layers of abstractions between you and the hardware, and you could do all sorts of very clever tricks with that. You really felt that your code was running on this hardware in very precise ways, and people were abusing the hardware to have more resolution than they should, to have more colors than they should, and they were finding all sorts of very impressive tricks. By the way, it's still going on. In 2024, you still have people finding new tricks on these old computers. And this is very exciting because you really feel as a software developer that you are in control of the hardware and you can directly talk to it. And it's no longer true nowadays, of course, and for good reasons, right? Because everything is connected on the internet. We have tons of security issues. And so we have to separate process memories. We cannot allow your code to directly talk to the hardware. And, even when you write assembly code for your CPU, it's not really what's going on the CPU itself, right? Because even the hardware has several abstraction layers. And by creating your own hardware, you can recreate the situation where you can, hack everything and do even crazy things. And for instance, the screenshot that you have on the right is actually a mistake in my linker script. I ended up with the code segment being executed in the middle of the frame buffer. And the fun stuff is that if you printf on your code, of course, you kill everything. And I don't know, I find it rather interesting that you can see your code being executed right there in the middle of your frame buffer and do maybe even a game out of this, right? And so that's what I mean by the freedom to hack. The third thing is to be able to experiment out of the box. And of course, it is well known in research, and we have people in this room who do graphics hardware research, who are using FPGAs or similar to emulate their designs, right? So it's a very nice tool to be able to rethink your hardware, imagine if I could take my algorithm, turn that into an actual piece of hardware, what would happen? How would it behave with the memory? How would it interact with the CPU? Where would be the bottlenecks? And it's a very interesting thought experiment. And by implementing your hardware on an actual FPGA, it's not only a thought experiment, you can actually run it and see exactly what's going to happen. And even though the FPGA has some overheads, so it cannot run at a very high frequency, because it's hardware, it's very precise, and that means usually the results you get would scale up if you were able to run it at, let's say, 10 times or 100 times the clock. So it does make sense in terms of the results you observe. All right, so what's the overview of the rest of the presentation? First, I'm going to give a crash course in FPGA. So if you're an expert in this, please bear with me. But I really want everybody to get a precise and clear idea about what an FPGA is. For a long time, I thought I knew what it was. But then when I really decided to investigate in it, I was amazed by what it truly is and the potential there is that I had completely missed all these years. Then I briefly touch upon the design language we're going to use because I will show you some code that becomes a chip, and I want you to understand the code I'm going to show you. And then we'll dive into some example designs. I'll talk about the community and the open source tooling, which has developed tremendously over the course of the past 6 to 7 years, and some conclusions. All right, crash course in FPGA. So we're going to talk about a digital circuit. In a digital circuit, you have physical wires, actual copper wires that encode your data. A ground level will be 0, and a VCC level, VCC is the voltage of your system, maybe it's 3.3 volts, for instance, will encode a 1. All right? So if you have 8 wires, they represent 8 bits, and that's a number. For now, we're going to assume this is absolutely perfect, and we have only 2 voltages, 0 and 3.3 volts. Of course, what you can guess from this sentence is that bad things can happen, and I'll show you a case, of course, of that. But in a lot of cases, maybe 95% of cases, you don't have to worry about the problematic issues. And of course, there is a clock signal because we're looking at a sequential design, and this clock signal is characterized by a clock cycle. And typically, designs are concerned with a positive edge of the clock. This is when it raises from low to high level. You can also do things with a negative edge. It's possible. Here is a picture of an actual picture of the die of the very first FPGA by Xilinx. And what I find very interesting about this picture of the actual circuitry is that it reveals a very periodic regular structure. If you have a background in texturing like me, this picture is probably hurting your eyes because you can see all sorts of periodic defects. And that's because this is indeed a grid of a same element being repeated over and over and over again. And let's call these elements cells. So we have many cells in a grid. And all these cells are, so to speak, alive in parallel. They're all constantly active doing things. Right? So now we're going to zoom in on one of these cells. One cell in an FPGA is composed of two things, a flip-flop and a lookup table. The flip-flop is taking the clock as input and is responsible for generating the Q output, of course using some other internal signals. The lookup table is responsible for taking the A, B, C, E inputs and generating the D output. Right? So let's first have a look into the lookup table. For the sake of clarity, I'm just going to consider two inputs because what I had before was a for loop. We're just going to look at a two-input lookup table. And in fact, the lookup table is implementing a truth table that tells you what should be the output D given the value of the input A and B, which is either 0 or 1. And so by configuring the lookup table in different ways, you can implement a XOR function, a OR function, an AND function, an AND, or whatever you want, whatever it is you want, just by simply configuring this lookup table. And this is the first thing that is configurable in an FPGA. There is a little bit of memory in this cell, which records the lookup table, and you can configure yourself this lookup table to choose the logic function implemented by it. Now, the important thing to keep in mind is that this lookup table is asynchronous. That means that whenever the inputs change, it tries to, as quickly as possible, update the D output. And this does not happen immediately. You have a tiny delay in picoseconds, but we'll see later that these delays will accumulate, and this might become a concern. Okay? But it does update immediately. Now, let's step back a little, and let's discuss the flip-flop. The flip-flop internally is connected to the D output, takes the clock as input, and generates the Q output of the cell. So to understand why the flip-flop is essential, we're going to build a little circuit. So we are going to set up the lookup table to output not A on the D output. All right? So if A is 0, D will be 1, and vice versa. Now we're going to connect a wire between the D output and the A input. So some of you might be starting to see the problem coming. What's going to happen here is that if A is, let's say, 0, of course, the lookup table will as quickly as possible output 1 on D, but because D is connected by a wire with A, it will become 1, which will again change the value of D, which becomes 0, which again becomes 1, and so on and so forth. And this is going to loop as quickly as possible, unfortunately, in a way that is not very stable. We talk about meta-stability in this particular case, and that's usually something you do not want, right? So what you would expect is a nice clean signal that goes up and down with some nice rhythms. This is not happening because this is an asynchronous circuit. What you get is noise. And so in 99.9% of cases, this is bad, and that's called a combinational loop, and the tools will blink red, telling you you have a combinational loop or combinational feedback loop inside your design. Please don't do that. There is one scenario where this is going to be useful, and we're going to look at it later on. So how do you resolve this problem? Well, that's where the flip-flop comes in. What the flip-flop does is that we're going to modify the circuit. Now I'm connecting the Q output to the A input. So what's going to happen here? Let's assume A is 0, D gets updated to 1, it goes as input to the flip-flop, but the flip-flop does nothing. It does not change the value of Q. It waits for the next positive clock edge, and when the next positive clock edge comes in, then it copies the D output to Q. In other words, it registers the value, the previous value of D until the next positive edge. Let's see how this works. A gets updated now, D changes to 0, the flip-flop does nothing because it registers the previous value of D, which was 1, and it keeps the value this way until the next positive edge, and there it reflects the change of value. So a flip-flop is a synchronous component that can act as a register because it remembers the previous value, and it's able to stabilize this circuit by becoming a synchronous circuit synchronized by the clock. Okay, and now you have a nice clean signal out of this Q gate. Okay, now we've seen everything we need to know about the cell. Let's zoom out a little. We have one cell, and now we have many cells inside this FPGA. Hundreds, thousands, millions on bigger FPGAs, right? So a lot of them. Some of the cells, of course, are connected to the outside pins of the FPGA. And by that, I mean the actual electrical connections outside of the chip, right? Some of them can be inputs. This is the case on the left. Some of them can be outputs on the right. And in our case, for instance, this might be the vertical sync of a VGA signal we want to generate to create a picture on screen, right? The cells are interconnected by routes, and these routes cross, and they cross on switch boxes, which are also configurable. And through the configuration of the switch boxes, you can connect the gates together, the cells, sorry, together, in any way you please, to produce a complete electrical circuit. And this is why an FPGA can become any hardware you choose, because it can implement the logic you want in every cell, and it can connect these cells in the way you choose to produce your circuit. All right, so let's, to understand something very important, let's look at this purple path here. This purple path is connected to the Q output of the first cell, then goes only through D outputs, these are the asynchronous outputs of the other cells, until it reaches the last one, where the pin is connected this time to the Q output. We call such a path a combinational path because it goes only through asynchronous circuitry. What this means is that when the value of Q will change, this path will immediately try to propagate as quickly as possible the signal through the switch boxes, through the cells, until it reaches the final cell. All right, so let's see how it looks. Positive edge, the value from the pin is copied onto the Q output. Signal propagates. It takes time because the cells have to look at their configuration, reflect the output, the switch boxes as well. This takes some number of picoseconds, and then it finally reaches the last one. Please pay attention at when the purple signal reaches the gate compared to the positive edge. The signal has to reach the final cell before the positive edge of the clock, because if it's late, you will not have the correct information on the output. All right? And this determines the maximum frequency at which your design can run. Because if it takes too long for the signal to reach this gate, you will have to use a lower frequency to ensure proper operation. So you do not get to choose your maximum frequency, not directly. What happens is the tool tells you, oh, the longest combinational path in your design takes that many nanoseconds, so your maximum clock frequency will be that much. Plus, it varies with chip temperature, which is, you know, what it is, because this is a physical device, right? And so that means that if you really want to be at, let's say, 25 megahertz because you're generating a VGA 640 by 480 signal, you have to make sure your design validates at a higher frequency than 25 megahertz. All right, so that's the first very important thing when you work with FPGAs or with ASICs circuitry, actual circuitry in general. Now, the cool thing, sorry, let me go back. The cool thing here, if you look at this circuit here, is that we have some free cells at the bottom, right? So we still have space. So we can fit more stuff in there. And it's fine to fit as much as possible as you want in the FPGA because everything lives in parallel. Everything is always constantly live. This is a fully, completely parallel crazy machine. And everything you can fit in there will be happily working jointly with everything else without any interaction if you want, or with some interaction if you create them in the graph. And so that means that as long as you can fit stuff into your FPGA, you're welcome to do more, and everything still happens all at once inside. All right, one last detail, which is very important when you deal with FPGAs. Within the fabric of the FPGA, the grid of cells, you have special circuitry, which we call hardened blocks. And these are hardware, like true hardware implementation, non-configurable implementations of some specific functionalities. One that is super important is the BRAM, the one you have on the right. This is extremely fast memory, which is embedded into the FPGA and distributed everywhere in the fabric. And this thing can answer to a read or write request in just one cycle at the maximum frequency that your FPGA can achieve. That's amazing memory. You never get to do that normally. This is a piece of memory where you present an address, next clock cycle, you get the answer, right? That's fairly amazing, and that's one very powerful aspect of FPGAs. The other important one is this DSP block. This is typically implementing multiply and add operations, because multiplications are using a lot of cells if you do them by configuration. So by having these blocks, you can implement arithmetic more efficiently in an FPGA. Typically, these are configured for floating point operations, but you can do whatever you want with them. All right. I thought the blinking was done. Take-home message on this part. FPGA is a grid of cells, lookup table plus flip-flop. The flip-flops are a barrier on the clock edges. They act as registers. The lookup table and the routing implements the logic. Everything happens all at once, and you have to worry about two things when you optimize your design: the space limitations and the max frequency you can reach. And this is the case of the slowest horse of the pack, because the longest computational path is going to reduce the performance for everyone. So sometimes it's better to spend more cycles than to try to fit everything in one cycle, because you're paying it with max frequency for everyone. Is it that simple? It is that simple. With that, you know 95% of the things you need to know. Of course, there are some more advanced topic and tricky details when you have multiple clocks and whatnot, but with that, you can already go a very long way. All right. Obviously, we are not going to configure by hand the hundreds of thousands of lookup tables and box switches of this FPGA. We need something else, and this is where the design language kicks in. Okay, so the two most typical design languages, and probably some of you have seen that in school, are Verilog and VHDL, and they are used to describe hardware. I won't be using them because it turns out I ended up developing my own language. I won't go into why, because I don't have time. This is a different topic, but I'm happy to discuss it with you afterwards. And this is the one I'm going to show you because this is the one I'm using for my designs. In all these languages, we write expressions that looks like code that actually describe a circuit. So when you write something like B equals A plus 1, you're actually describing a circuit where A is a bunch of wires, plus 1 will create logical gates that implement an increment, and the output of this is another set of wires, which is called B, right? And so with B equals A plus 1, you do implement an adder, which will end up being a circuit. Now, this code is given to a tool that synthesizes the logic. We don't talk about compilation because things are a bit different. And this logic is actually a graph of all the little gates that implement your design. This graph is given to another tool, which is placing each of the little gates into the cells of the FPGA, configuring them appropriately with the right logic function, and then routing is optimized to connect everything. Needless to say, these are highly combinatorial optimizers, which are very difficult problem to solve for. This is slow, right? This can take minutes, this can take tens of minutes, this can take days on big FPGAs, right? So it is not like compilation where you just, change something, compile, test. No, because here you have to wait for a very long time. Some of the designs I'm going to show you take like 45 minutes to synthesize, for instance. You can simulate. The tool knows how to generate many operators like adders, multiplications, shifters, comparisons, and so on and so forth. And they also know how to generate choices through multiplexers. So, if condition A or B, I'll come back to that later. All right. Let's have a look at an actual design structure. So in my language, Silice, when you write, what you do write is called a unit. A unit is a blueprint for a circuit. This blueprint will get instantiated to become an actual circuit whenever you want, and you can instantiate it multiple times if you want to duplicate. Side note, if you have designed a CPU and you want a quad core, you just instantiate your CPU 4 times. So that's as easy as it gets, right? Which is quite amazing if you think about it. So the unit has a signature, and the signature is describing the input and outputs. This one is called LEDs because these are actual pins on the FPGA which connect to tiny LEDs. We have 8 of them, and uint8, as you expect, it designs an unsigned integer of 8 bits. If you want 11 bits, you can. If you want 133 bits, you can. Then you have a number of declarations. These are variables. They may or may not become registers, depending on how you use them. Then you have an always before block that is describing what should happen at the start of every cycle. Then you have an algorithm block, and this is where things diverge significantly from, let's say, Verilog or VHDL, because you can write an algorithm in imperative programming style, which makes it much easier than reasoning between 2 clock cycles. Right here, you can really describe things as a flow of steps being created. And then you have an always after block, which is something that is done at the end of every cycle after anything that was done by the algorithm. Okay? Let's look at an actual example. Here, we're creating a small unit that outputs on the LEDs. We're creating a 24 bits counter. We have an infinite loop. It's perfectly fine. It's a circuit, so it's always on, right? So as long as there's power, this loop will run, and that's okay. If you create 2 instances of that, they will both independently run, no problem at all. Then we take the 8 most significant bits of the counter and output them on the LEDs. And finally, we increment the counter. We have just implemented the hello world of hardware design, which is called a blinky. And if you run that on an FPGA, you will see little LEDs blinking. Right? And that's why usually you have LEDs on board, so that you can have a blinky and you know things are at least working reasonably well for the basics. All right. Last point to keep in mind. This is not a program. This is a circuit you're describing with code. And that means that everything you do is taking up space and impacting the max frequency. Here I put the operators in rough order of cost for both space and max frequency. And believe me, after a while, when you write this multiply sign in your code, you feel the weight of it. You're like, I don't want to write this, right? Because you know it's gonna be bad. Unless you have DSP blocks, which is a big luxury. And there is also no such thing as not doing something. So it's exactly like in a GPU, when you are running lockstep in a warp, if you do a conditional, if C, A or B, both are being done anyway, because they are both a piece of circuitry. And what happens is that the conditions becomes a multiplexer that is choosing between them. And as a programmer, this is something that is very difficult. You need to not do too much. You need to let it go. If it can happen all the time and you just look at it when it makes sense, that's fine. Because you will pay a higher price by trying to be clever and to not do something. Right? That's why some hardware design can be a bit confusing as well sometimes when you look at them. Okay, here is an actual case. This is implementing the voxel renderer of the game Comanche, which was released in 1992. This was, of course, in pure software. Here it's in pure hardware. On the right, you can see the full code of the rendering algorithm. This algorithm, as a side effect, is filling in the frame buffer that is being displayed on screen. And there is another part of the circuitry that generates the VGA signal. If you look at this code, you have a while loop. Again, an infinite loop. That's okay because it runs all the time. Then you have another while loop that goes from front to back. That's how this algorithm works. Then you have another loop that goes from left to right in each of these steps. And if you look carefully here, you will see 2 blocks that are very similar. These are lookups into the height map. And there is a plus plus semicolon operator. And this operator is telling Silis, I want to wait 1 cycle. Why? Because we're accessing a BRAM, which is storing the height field. And so we're setting up the address, waiting 1 cycle, and getting back the result. Right, this is what happens here. And a similar thing is happening here at the bottom, where we write the result in the frame buffer. And this is how this algorithm operates. Okay, now let's look at some more designs. So the first design I'm going to talk about is a fairly big affair, which is a complete architecture. And I called it the Doom chip because that's what it is. It's a hardware chip that does only one thing, that's rendering E1, M1, which is the first level of the game Doom. It can do other levels as well, but I'll mention it afterwards. You can see the hardware here at the bottom. It's implemented on the FPGA board, and then the weird thing on the breadboard is actually the VGA DAC, which converts the N bits, I think it's 6 bits of the RGB signal into an analog value. All right, so the Doom renderer is different from the one in the game. because I customized it to fit better the hardware. And also I cannot reuse the source code of Doom anyway, because I'm redoing everything in hardware, right? So there's no CPU to run any code. There's no CPU in this design. So what it does is it's recasting res in the scene. The scene is a binary space partition tree in 2 dimensions as seen from above. And when you recast, you have a very nice property, which is that you're going to create columns from the top that grow downwards, from the bottom that grow upwards as you encounter the walls. And the red segment is the current open segment. This segment is only shrinking, only strictly getting smaller until it closes, because the level geometry is normally guaranteed to be closed, right? And so that's how it works. It's rendering 1 column of the screen every time. As soon as the column is done, it writes it to the frame buffer and moves to the next. So here is the full architecture. The first block I'm going to talk about is the texture unit. And I think an interesting detail of the Doom chip is that the hardware is built from the game data by the preprocessor. So take a second to process this. I'm talking about data-dependent hardware. The hardware will be different if you generate it for a different level of the game, right? So that leads to quite interesting possibilities in terms of optimizations, of course, even though the Doom chip itself does not really do that, apart from selecting exactly the set of textures that is required for the level. And these textures are stored in BRAM. We don't have a lot of BRAM, so unfortunately in this version, the textures have to be downsampled. But then the texture access is extremely fast, of course. Then we have the renderer that similarly encodes the level data, and it performs a traversal in the BSP tree in order to create the spans which are drawn in the column on screen. And once the column is ready, the column is sent to the memory arbiter, which is talking to an SDRAM controller, which sends it to the actual SDRAM chip. By the way, I have the card which is running the Doom chip here. The FPGA is here, and the SDRAM chip is on the side. So the chip is really outside. And so the controller has to deal with all sorts of interesting issues talking to this external chip, right? And so why do we have a memory arbiter? That's because we have a second thing that is accessing the frame buffer. This is the chip generating the video signal. When you do a video signal, you don't get to take your time, because the video signal is doing what it is doing, and you have to run after it and make sure the data is ready when it is required, right? It's called racing the beam. I'll show you some other examples. Here we have a frame buffer, so we don't truly race the beam, but we still have to fetch the data from the SDRAM. And believe me, when you do hardware, memory is slow, right? External memory is very slow. You have to wait tens of cycles before you can start reading data. And so that's really a thing you want to avoid. So what this video chip does is that during the blank interval after every row of the video signal, there's a blank interval where nothing happens. During this interval, it takes priority, goes into the SDRAM, and streams the data as fast as possible. And you can see there's a 128-bit interface to the SDRAM to pull data as quickly as possible. I have another version where I was able to increase the bandwidth to 512 bits thanks to properties of the SDRAM chips, which can pipeline their accesses and so on. I won't go into details. But there are very interesting ways you can use these chips to be more efficient. And once it has the data, it stores it in 1 row of BRAM, and then when it generates the signal, it does not need to access the SDRAM, so the SDRAM is free so that the renderer can write. The arbiter is necessary because you have 2 chips communicating with the same SDRAM controller, and this can't happen, right? You have to have something that selects between them. If you write code in Rust has this concept that a resource can be owned only once by a thread. Well, this is what happens in hardware, right? Because you have 2 wires, so anyway, you have no choice. You need to implement these arbiters and so on. And so the arbiter also implements priorities for the video frames. That wasn't me, I think. All right. So here's version 2 of the Doom chips. This is mostly the same, but this one is using SDRAM to store all the data so that you can have one design and don't need to regenerate the design for different levels. As you can see, it's still running quite fine. This is a 50 megahertz design on a fairly fast, well, this FPGA has a fast fabric, which means it's fairly, even if you have long combinational paths, it's still, it can still run at quite high frequency. And yeah, everything works, right? You can see we can take the lifts, we can switch things, you have the light dampening. All of that is done in hardware. There is no CPU at all in this design. It's all a gigantic chip. And congratulations, you're at the end of the level. All right. So what I just said might sound a bit weird, right? I mean, what do you mean by it does a single thing, right? If you were to do an ASIC, an actual, fabricated chip, this would be extremely wasteful because you're not going to do one different, I mean, this costs a lot of money, so you're not going to do one chip per level of a game. Sure, but we're on an FPGA. FPGAs are reconfigurable and they can be reconfigured very quickly, milliseconds. In fact, an FPGA can even choose to reconfigure itself towards a different design. It's called a warm boot. So that creates very interesting possibilities where you can hot swap the design of your FPGA depending on the task at hand. And so here in this case, you reach the end of a level, you pull the switch, the FPGA warm boots to the next level, and there you go, right? And so that's how it's possible. So the Doom chip is a fairly big affair. It takes 25,000 cells on an FPGA, which is still only 30% of this FPGA, but that's quite a fairly big FPGA. More importantly, what I find inelegant about it, in retrospect, is that the utilization efficiency is fairly bad. And the reason is in the renderer, you have a big algorithm with many steps, right? And if you think about the way the cells are used in the FPGA, only a small percentage of the cells are actually useful at any given cycle because you have this gigantic multiplexer that selects only, this little slice of cells that does something useful. All the rest of the design does stuff that gets ignored, right? So that means that in terms of utilization, we are not really exploiting the FPGA as much as possible. Yet, if this answers your needs and fits your purpose, there's nothing wrong with doing it, right? If you have the frequency, if you reach the frequency you desire and it fits your FPGA, that's fine. But, it would be more elegant to try to push a little bit the efficiency. And this is what we're going to do now by discussing pipelines. Not on Doom, on different things. All right. Quick refresher on pipelines. I'm sure you've heard of pipelines in the concept of CPUs, but these are just, computational networks where you have a number of stages. Here, stage 0, 1, and 2, which are shown vertically. And you have a bunch of data that has to be processed by the pipeline. And, A, for instance, will have to go through step 0, step 1, and step 2 before we consider that it has been fully computed. We have the time from left to right. So at the first cycle, stage 0 is empty, so A enters the pipeline. At the second cycle, A moves to stage 1, which frees stage 0, so B can enter stage 0. At the third cycle, A enters stage 2, which frees stage 1, so B can enter it, which frees stage 0, so that C can enter it, and so forth and so on. Next stage, here something interesting happens. A exits the pipeline, right? From now on, every clock cycle, a new value exits the pipeline. So from now, we have one result every clock cycle. Okay, and now the pipeline is empty and ready to answer more requests. An important characteristic of a pipeline is the latency. This is the time it takes before you get your first result. But the very cool thing is that if your stages each take one cycle, then you get one result per cycle. All right? The other thing to notice is that at this particular moment, we have a full utilization of the pipeline. All stages are active, so you're fully using the hardware. If you add more data, you would see that the head and tail are quickly amortized, and you get a very nice utilization of the hardware. Here is the syntax for a pipeline, just so you can understand the code I'm going to show you afterwards. You have little arrows that mean your data goes to the next stage, and everything else happens automatically. And here is the kind of things you can do. This is a 1080p real-time remarcher that performs 190 remarching steps per pixel, which is rendered at a guaranteed timing of 60 Hertz. And it runs at a 173 megahertz clock, which is given by the video signal itself, right? Let me show you this again. So it's truly marching 190 steps per pixel, and yet you have the result being displayed in guaranteed time on screen. So let's have a look at the code. Let's first have a look at the principle. So if you implement a remarcher taking your time, you would do an external loop on the pixels. Then given a pixel, you would do a loop on every step where you march. Let's assume we do something non-opaque so that we don't stop at the first hit, and you will walk along this way. Then you go to the next pixel, and again, you march along it. And this is, of course, super slow, but that's the basic principle of a remarcher. Let's now look at a pipeline version of this. we are going to create a pipeline with one stage per step along the array, right? So here we have 4 marching steps, so we have 4 stages into this pipeline. The first pixel will enter the stage 0 of the pipeline. Then on the next clock cycle, the first pixel moves to stage 1, freeze stage 0, so the second pixel can enter it. And then the same occurs at the third cycle. The third pixel enters stage 0, the second pixel moves to stage 1, and the first pixel has moved to stage 2. And you recognize probably the same diagonal pattern as we had on the previous slide explaining the pipeline. All right? Until we reach the end. Now, notice what happens if I run this again. The first pixel enters, and now, pop, 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 we have 1 pixel every cycle outputting the pipeline. That means we can raise the beam. Because if we time everything right, when the video signal says, I need the first pixel value, it might be just when it exits the pipeline. And then every clock cycle at 173 megahertz, we have a new pixel coming in, even though we march 190 steps along this array, right? Which is no small feat, even on a modern CPU. All right, so of course we have to deal with latency. So let's have a look at the code. Here is the code. I just hid some parts so that it fits in the slide, but it's a very simple affair. Here you can see 3 arrows, which are creating the pipeline stages. However, here, this is a loop that goes over all pixels, so this feeds the pipeline with pixel coordinates so that the remarcher can start. So this is what gets the data into the pipeline. And here you have a block which is using the preprocessor of Sylvain to generate code so that this gets unrolled in the 190 steps, because every step is the same. And so this loop is unrolling and writing the code for you so that you don't have by hand to copy paste 190 times, which would be a bit horrible. And that's it. And with that, you have your complete pipeline. There's one small detail, is that you have to wait the perfect amount of time so that the first pixel arrives when it is needed by the video signal. Otherwise, your frame is going to be off by some amount. So this gets a bit tricky to set up. But in simulation, you can test and find out the right delays. All right, hopefully that was clear. The cool thing with this is you get a very high max frequency, because in a pipeline, you have a lot of registers between every stages. And so you have very short combinational paths. So you can usually get a very high frequency. And on an FPGA, because you have flip-flops everywhere, you have registers everywhere in the fabric, the pipelines are very well suited for that. That easily outperforms even a modern CPU. Granted, I haven't implemented a super optimized CPU version, but there's 2 orders of magnitude in performance, and the CPU would have to fill a frame buffer. We do not have to store anything in any memory. We do not have to worry about bandwidth or anything, because whatever we compute goes directly to screen, right? And in terms of resource usage, there's an interesting discussion to have comparing a pipeline version versus a parallel version. The bottom line is that in the parallel version, you need memory as well, and that's a problem. All right, it turns out the exact same pipeline, with some adjustments, of course, can solve partial differential equations using the random sphere approach, or the random circle approach in 2D. And if you don't know what this is, there's a very nice paper called Monte Carlo Geometry Processing by Shoney and Crane, which explains this super nicely. So what happens is that at every pixel, you have to randomly jump around according to some radius, which is given by a distance field, to solve for the PDE, which is in this case a diffusion equation. So that's heat transfer. This is being done in real time with guaranteed timing directly to your screen in hardware, right? And the noise you see is because this is a random walk. And this randomness does not come from a pseudo-random generator. This randomness comes from something called a ring oscillator, which is exactly the bad thing I told you not to do, which is a combination loop. Because here, if you set it up properly, you can get randomness for free. And this is what happens here, right? Of course, it would be nice to smooth out this noise by accumulating in a buffer, but I don't want to have memory. So I'm, hoping that our eyes will blur out the thing for us. It's not fast enough for that, unfortunately, even though this runs at 60 Hertz. All right, final note on SOCs and computers, because so far I've showed you designs where there were no CPUs, but it's also fun to have a CPU. And in fact, as I was doing the Doom chip, Sylvain, who is an expert designer, very active in the FPGA open source community, released this design. This design is a computer, right? So it's purely CPU based, but it's a super well done architecture that exploits this tiny board that I have here. And this tiny board has a very small FPGA, which is only 5,000 cells. So that's pretty small. And it has a little bit of memory on the side. And with this, he is able to run at 25 megahertz to run this source port of Doom. And believe me, this is quite amazing to see. And this shows what happens when an expert really takes to optimizing the design to fit the FPGA and to have a very nice resource utilization. So, this made me realize that I should really try now to play the game of getting things more efficient and smaller. And this is what I did. And I ended up implementing on the exact same FPGA a CPU, which is a RISC-V CPU, plus a GPU, which is a bespoke GPU that performs perspective correct span rendering, textured span rendering that are used by a modified version of Doom to have a GPU accelerated Doom on this tiny thing. Right? Remember that Doom was running great on a 66 megahertz 486 initially, and here this is a 20 megahertz thing with only 5K loots and some DSPs. Okay, there's a little trick here. All right. You can get even more efficient on smaller FPGAs. This is on an FPGA that has only 1,280 cells, and on that you can fit a 32-bit processor. Again, the simplest RISC-V form of processor. That's a processor for which you can compile with GCC. You can take your code, compile it with GCC, and run it on this thanks to the RISC-V ISA architecture. And what you see on the left is the entire code of the dual-core CPU that runs this. It's a very special type of dual-core. It's a barrel CPU, right? But anyway, it's great because I can have one core for the music that you don't hear and one core for the graphics in such a small footprint. There are even smaller CPUs. People do very impressive stuff in this field. All right, a few words about the community. First, everything I showed you is powered by amazing open source software, which emerged, I don't know, maybe 7-8 years ago, but which is now starting to work extremely well. So if you're an expert in FPGAs, but haven't looked at the field in a while, this stuff is absolutely fantastic. So Yosys is the software that generates the logic graph. NextPNR is the software that will place and route for an FPGA. It doesn't support all FPGAs because these guys have to do reverse engineering of the FPGAs, right? They're not really helped by the vendors. And so they don't support all FPGAs, but the boards I'm going to give you links for afterwards do support these tools. Verilator and Icarus Verilog for accurate simulation. You don't even need a board to start working. You can do it in simulation on your computer, and Silis nicely supports that, including graphics output. Of course, the RISC-V ISA architecture, this is fantastic because implementing the simplest norm, you can compile with GCC and G++. There is a full tool chain for them for RISC-V, and you can progressively make your CPU more complex, adding multiplication and division, moving to 64 bits, moving to multi-threaded and everything. But you can take it step by step. This is truly amazing stuff. And then Litex, Idealize, GTK Wave, Wall, all sorts of cool software that I would be happy to talk about, but I unfortunately don't have time. The boards, a lot of very talented enthusiasts and makers are creating boards with these small FPGAs. These cost from a few tens of dollars to maybe $200 or $300 at most. The ULX3S and ECPIX5 are using a fairly big FPGA, which is this is a ULX3S I have here, and the other boards are using this small ICE40 UP5K FPGA that has 5,000 cells. It's a very good starting point if you want, because it's big enough that you can comfortably get started, and it's small enough that it gets very interesting to optimize on it. And then, of course, some commercial boards and many others. Oh, by the way, the FOMU here is a tiny board that fits into a USB port. Quite amazing. I didn't take it because I'm losing them every time. So The languages, I talked a lot about CDs, of course, because this is mine, but there are great other HDLs out there, like Pipeline C, Spade, Defiant, Amaranth, Migen. You really have to look, the ones that you will enjoy the most, try them out. To me, it's really a matter of taste and to select the one you're comfortable with that will let you achieve your goals. Of course, there's Verilog and VHDL as well, if you want to go the purest way. Many projects, I won't go through them. Please take a picture or come back to the slides. Amazing stuff done by the community. The only one I really want to mention is Tiny Step Out, because this is a project where you can take your designs and create an actual chip in a foundry out of it. They amortize the cost by sharing the fabrication across many users, and it's active. You can submit a design now. I think the next one will be fabricated in 24 days, if I'm not mistaken. Amazing stuff. All right, concluding words. So this is really a fantastic field to explore. It's extremely rewarding when you get your hardware to finally run. Debugging is an absolute nightmare. You have never done anything that hard in your life, but this is great, right? When it works, it's absolutely amazing. And there are tricks to have things a bit easier, like simulation, of course. You will learn a lot of things. You can contribute back. I think as graphics people, we have this, gift, which is that we can make very engaging demos, things that look good, that get people interested in something, and that's a very powerful trick to bring to the table when you enter a field. And this stuff will really change your perspective on computers, right? So I like to say that now I look at CPU the same way a game engine developer is looking at the scripting engine, right? The CPU is this very slow machinery that I really don't want to talk with because I want to do coprocessors which are super fast. Of course, I'm being a bit caricatural, but that's somewhat true. All right, thank you very much. There are many projects I would like to talk about. I didn't have time. Please feel free to ask questions about them if you want. Thank you again.
Thank you so much, Sylvain. That was really inspiring. Really fun. I already have a question here.
Hey, thanks so much for the talk. It was really great. So I'll start with the rude part of my question, because it's easier, and then I'll extend on that. The rude part of my question is, what are you using this for? But I want to explain. So typically in industry, like everything that we're actually shipping and building at scale, either ends up not having an FPGA because pipelines are fixed and power management is hard, and generally there's a lot of inefficiencies there, or when they actually ship, they ship behind an API, like in Next Silicon's case, where they ship like a giant FPGA somewhere on a data center and you don't see it. What do you imagine for the industry that can actually make these tools mainstream, if they're even meant to be mainstream and not just prototyping tools?
Right. Yeah, that's a very fair question. I'm not looking at this from the industry perspective. I'm looking at this more from the maker, hobbyist, enthusiast perspective, and someone who wants to learn about hardware. I'm concerned that in 10, 15, 20 years from now on, it's going to be very hard to get anyone to do the actual hardware we need our software to run on. I'm concerned that development will lose this connection with hardware, which in my eye is very important. And even if it's only for 1% of the developers out there, because of course not everyone needs to know the gritty details of the hardware, I do think it's important that we take the time to prepare this future where we need to educate people about hardware. We need to get them excited about the low-level stuff. We need them to get excited to write software that talks to the hardware in interesting ways. The other thing I think that is interesting here is that when something becomes that easy to do, that you can do it at home on your desk, I'm thinking 3D printing, right, which is my field of origin. 3D printers have been around since the 80s, and for a long time, not so many people cared about them because these were, difficult to operate, very expensive, completely locked, and so on. Now, like I told you, you have the possibility to create an actual chip, an actual ASIC for maybe $100, right? It's insane, right? And so I'm not sure what it means for the future, but it means we are enabled with superpowers, right, to create these chips ourselves. And that's super exciting. I think we need to start thinking about how we make this engaging and appealing, and how we'll use this later, I'm not sure. But I think for small companies, it's already super interesting. If you have a startup and you want to experiment with something, FPGAs are reconfigurable, which gives a huge advantage versus many other hardened things. And so I'm sure some cool applications will follow. Yeah. And of course, FPGAs are used in many industries. I don't want to enter this, but yeah. Thanks. Mm-hmm.
So my question actually will very nicely connect to what you just said.
Okay.
And I've been also super impressed, for example, with microcontrollers. I remember like 12, 15 years ago, like they would be pretty expensive, especially the SP ones. Tools would be super painful. And now you can buy something like full kit for $10 on Amazon. It's
Yes.
And tools are amazing. And you connect it and it just works.
Yeah,
so
yeah.
I totally agree. But I also totally agree with this perspective on education. And my background, like studied 15 years ago, a mixed EE and CS program. So we did everything from making our own transistors through like electric circuits, gates, FPGAs, etc. And I personally really enjoyed it. But lots of my colleagues were like, no, not really. We want to go to SQL and PHP and, some stuff that will give us jobs and make us money. So I'm wondering, like you as such a seasoned also educator, like how this perspective has changed over time. Is the interest increasing because now everyone is using some virtual machine languages that this is so exotic and cool that people are more compelled to do this? Or the opposite, that it's so abstract and unrelatable to their job that is, like how is it changing over time, and how do you think it will progress?
So it's a very good question. So the thing is, I'm nowadays I'm teaching this kind of stuff, but it's very recent. So I don't have a lot of history doing this. What I can tell you is when we put these boards into the hands of students. So one of the projects we do is a small music player with a screen so that they can display a picture and have fun listening to their music. They get super interested in it because they do this artifact that is useful for them because they can listen to music and it makes sense to them. They connect to it, right? So I think this is the fact that it is easy and that it is accessible is going to increase the adoption of that for educators. Now, what I can talk about, however, is a community. If you look at what people do, it's a lot of young people spending a lot of time doing boards, doing PCBs, doing hardware. I'm actually amazed at the amount of expertise and knowledge these guys have. You were mentioning microcontrollers. There are things like the RP2040, which costs like just a few dollars and is like a 200 megahertz dual core, like crazy thing. It's absolutely amazing. So I think things are looking good in terms of getting younger people excited about it. But I'm not sure about the standard curriculums. Also, in France, for instance, we learn computer science somewhat separated from electronic engineering. So I was never trained, for instance, on this. I had no clue about Verilog, 7 years ago, right? For instance, it's not true everywhere, but I think it's a problem, and I think this has to change, and this hopefully will trigger some changes in this space. Yeah, I'm not sure I answered, but tried my best. Okay.
Seth? There we go. Hi. So it was a lovely talk. I'm curious, kind of a corollary to this, how has this changed your approach to your own relationship with computing, like the actual devices you use for your work? I think it's maybe not uncommon, especially for those of us who grew up in that period, to I have a dream, I'll retire and I'll build all of my own hardware and my own operating system, and it'll be lovely, and I won't use other people's. Do you find yourself going down that possible trap and or lovely experience?
No, to be honest, no. I think what has changed is the degree to which I am impressed by modern hardware increased by several orders of magnitude. Modern hardware is absolutely nuts, right? And I've been using GPUs since they basically exist, and I think I have no idea how powerful these later GPUs are. It's crazy what you can do on them. And one of the things that in terms of education is important here is to get people a feel of what should be their expectations in terms of power. I mean, 20 megahertz is still 20 million things per second, right? And nothing should be slow at 20 megahertz. So can you imagine at 4 gigahertz on 32 cores, right? So I think this is also where there is a disconnect that was created, and getting back to hardware helps me, reminding myself about what my expectations should be in terms of performance. And really, in terms of hardware with GPUs, CPUs, we live in crazy times, right? And we should be aware of that, and we should be fully exploiting that. And I mean, we all know that a lot of power is wasted in perhaps necessary abstractions, but it's also important to remember this. So no, I don't really get into this. I don't want to touch other things anymore. For me, it's more like I would love one day to be able to create coprocessors that can blend into my everyday usage. I have a few ideas for that. And that would be, truly useful, not only for exploration, but for actual use. Maybe having an FPGA alongside a CPU, but I do realize there are tons of challenges with that. I don't know if it's going to happen, but this would be great. Yeah.
Thanks. That's a very, very interesting talk. And my question lies on the Sylvain language. Yeah.
Uh-huh.
I will see immediately note that the Sylvain has a language design construct called the algorithm, and for me it seems to be seated somewhere in between, say, Verilog and high-level synthesis.
Yes.
And when I was using Verilog, I find it very, the code was overall not that tight, and I have to repeat the code, say module input, blah blah blah, output, blah blah blah, anywhere, paste them, copy them. Yeah. And when I was using the high-level synthesis, I think it abstracts too many, too many processes away, so I can't easily control the, say, the stages that the eventual computation will be like. And so in Sylvain, how do you balance those the design efficiency and the control over the actual generated circuit? I found it very interesting.
Thank you very much. This is a perfect question for me to answer. So let me answer you here. On the left, Verilog. On the right, high-level synthesis languages. Here's Sylvain. So Sylvain is inspired by my experience with shader languages. So to me, in a way, Verilog is register combiners, right? And Sylvain is like CG, or the first version of GLSL. It is very close to the hardware constructs with just a little bit of comfort added to it. Plus this idea that you can reason in terms of imperative programming and data flow in pipeline, as opposed to reason from clock cycle to clock cycle, which is fine for many things like controllers, but which can get very tricky when you try to make more complex algorithms. And you can blend all these styles together. You can write algorithms that contains pipelines that contains algorithm, and this is all fitting together, I think, fairly nicely. But of course, I'm not very objective, right? So, but you are very close to the hardware. I mean, C to hardware is very impressive. There's great work being done here. No question about this. There's also OpenCL to hardware and all these kind of things, and they're great and they're super interesting technically. But I don't want to use them because I like to be close to the hardware. That's why I'm doing this hardware design thing, right? So yeah, thank you very much for the question.
Wow, thank you for the answer. Very impressive.
Thank you.
Yeah, so thanks for the great presentation. So I am not a hardware guy, so my question could be stupid. But do you think FPGA can outperform the current GPU architecture for some specific tasks? For example, if we can switch the implementation of some ray tracing cores depending on the scene on the fly, it would be great for optimizing the hardware usage. So do you think such optimization could be possible in the future?
So this is an excellent question. To be honest, I think beating a modern GPU on its own ground is not going to happen. But then you have to also consider what is your metric. is your metric raw performance, or is it, for instance, performance per watt? Because if you do performance per watt, I mean, this board is super tiny. It doesn't use a lot of power. On top of it, my understanding, I'm not expert at this, but my understanding is that the power usage depends also on what you do on the FPGA itself. So in this respect, FPGAs are very hard to beat. So it really depends what your exact metric is. Also, there are cases, the one on the left here is a solver, a constraint-based solver to solve tiling assemblies. This is a wave function collapse or model synthesis for those who are familiar with this. And the cool thing is the hardware here is creating bit comparators to solve for the constraints, which have a weird size, like maybe they're 67 bits, right? And this all gets resolved in one cycle, so you get very fast propagation and everything. And because it's highly specialized, I don't think it's going to beat a GPU, but a CPU, yeah, probably, like the pipeline thing we saw. So yes, it's a complicated question to answer. It's a very good question. It's a complicated one. But in terms of wall clock performance, I doubt I can beat a 4090. It's not going to happen.
Thank you.
Not yet, at least.
Okay, we'll have to stop here because of the break, but Sylvain will be here still during the conference. We can talk more. Again, let's thank Sylvain for the
Thank you very much. Thank you.